In this vodcast, we're going to derive the composite property for cosine. And this is used, well, for one thing, it's used to derive other composite properties. It's also kind of the inverse operation of the linear combination process that we did before. In any case, if you haven't downloaded the Exploration 5.2c handout, then you should do that. You should pause and do that right now so you can follow along and take good notes while we do this. Okay, in this picture here, we have two pictures. They are both pictures of angle A minus B. In the left-hand picture, we have angle A in standard position with its terminal ray right there, and angle B in its in standard position with its terminal ray right there, and the angle between those two blue rays is angle A minus B. In the right-hand picture, we also have angle A minus B in standard position itself. So these two rays are represent angle A minus B. Same angle A minus B in both pictures. We also know from lots of stuff that we've done before, in the unit circle, the coordinates of on the unit circle where the terminal ray crosses the unit circle, the coordinates there are the cosine and sine of that angle. So those are the coordinates of that point, cosine A, sine A, and down here that would be cosine B, sine B. All right, then we have a chord drawn between those 2 points, and it's labeled D. And you might remember this, you may or may not remember this from algebra, but the distance formula for 2 points in the coordinate plane, we could draw this right triangle, and this distance here, this is just for some general point, would be y1 minus y2, in other words, the rise. And this distance here, this side of this triangle, would be x1 minus x2, where those are the coordinates of the point, and that would be the run between there. And we have this right triangle, so we would get x1 minus x2 squared plus y1 minus y2 squared, and if you wanted to find the distance between those 2 points, you take the square root of that. That looks just like the Pythagorean theorem, and in fact, that's what it is. We're going to leave it as d squared right now because we're just using this as a way to derive this formula, and that will be the most convenient thing to do. So to find d squared, in this particular case, I'm going to just use that distance formula. D squared is equal to x1 minus x2. Well, that's cosine A minus cosine B, and I square that, plus sine A minus sine B, and I square that. I'm going to expand all this, and I get cosine squared A minus 2 times cosine A cosine B plus cosine squared B. And then I'm running out of room, and this is also going to work out nicely. I'm going to continue on the next line. Sine squared A minus 2 sine A cosine B plus sine squared B. That's the whole mess. There's 6 terms there. And by the way, if you're not sure about my expanding of this cosine A minus cosine B squared, or sine A minus sine B squared, you should pause and do a little algebra refresher on your own about expanding binomials by FOILing them out, or however you want to do it. It's nice to know a quick way to do this. It's very handy. Okay, so that's d squared still. Here's d squared. I'm going to simplify things. Well, Hey, how convenient. I got cosine squared A, and then down below that, I've got plus sine squared A, and we know that that's a Pythagorean identity, which is equal to 1 minus, and then I've got all this stuff, minus 2 cosine A, cosine B. Can't do anything with that. 2 minus 2 sine A, cosine B. How did that get in there? I got this messed up here. This should be sine. You probably noticed that already. And when is he going to figure that out? Here, I just figured it out. That's supposed to be sine A, sine B. And this is supposed to be sine A, sine B here. So let's fix that. Sine A, sine B. And then I've got cosine squared B plus sine squared B, and that's plus 1 again. So I can do one more thing here before moving on to the next picture. And 1 plus 1 is 2. 2 minus 2 cosine A cosine B minus 2 sine A sine B. By the way, you're not going to ever be asked to do this, but you should definitely be following along. Make sure you've got this figured out. You understand what's going on. Okay, so looking at the next picture, this is also angle A minus B. That chord is still the same chord D because these are the same angle A minus B, and as we know from geometry, equal angles cut off equal chords in a circle, so those are equal angles in a little bit slightly different position. So now I'm going to figure out D squared again using the coordinates of the points now. So these coordinates would be cosine A minus B, sine A minus B, and down here the coordinates would be 1, 0 on the unit circle. So I'm going to go through and do D squared again using these points, using the distance formula. So I've got parentheses cosine A minus B minus 1 squared plus sine A minus B minus 0. I'll write that in, but we don't need to actually, squared. Okay, so I expand all this and I get cosine squared A minus B minus 2 times cosine A minus B plus 1. Okay, I'm running out of room again. Plus, now that's just going to turn out to be sine squared A minus B when I square that right-hand thing, since the 0 goes away. Here's D squared. Here's D squared. Let's see if we can simplify that a little bit. Hey, cosine squared A minus B plus sine squared A minus B is equal to 1 minus 2 cosine A minus B plus 1. Again, 1 plus 1 is 2. Last time we checked, so 2 minus 2 cosine A minus B, and that's D squared. Now we have two different expressions for D squared. That means we could put those together, set them equal to each other by substitution or the transitive property, however you want to think about that. Let's do that. So I'm going to put these two things equal to each other. 2 minus 2 cosine A, and then we're going to just see what develops here. When we put these together, what things will go away, what things will simplify in some ways or another. This is deriving. This is the process of deriving these things. 2 minus 2 cosine A minus B. Well, you probably already noticed that there's a 2 on both sides that we could subtract from both sides and get rid of. Minus 2, minus 2. Then I've got negative 2 cosine A cosine B minus 2 sine A sine B is equal to minus 2 cosine A minus B, and I hear you are already thinking of dividing everything by negative 2, and right you are. So divide each term by negative 2. That's going to turn, all these terms were all negative, and now they're going to all be positive, and the 2's are all going to go away. So let's see what we get here. Cosine A cosine B plus, is all that canceled out, turn that to a plus, turn that to a plus, everything canceled out. Sine A sine B is equal to cosine A minus B. So now I can, if I knew, well, I can go back and forth with this property, but this is called the composite property for cosine A minus B. That's it. Now, again, you should know how to use this. You don't necessarily have to know how to derive it. Hopefully you followed all that. I'm going to give you one example of how you use this to express as a linear combination an expression like this. So this is kind of the inverse operation of what we did with linear combination. This is not in linear combination form, but let's say for some reason we want to put it in linear combination form. Okay, we could do this. Well, first off, we're going to use this property that we just derived, and we could write this down. Y is equal to 20. Okay, I got the 20 there. But this thing inside here, I'm going to replace that cosine theta minus 60 with using the composite property. So in this, theta is the same as A, 60 is the same as B, so I'm just going to replace the A's and B's with thetas and 60s. So I get cosine theta cosine 60 plus sine of theta times the sine of 60. All right, in those brackets, there's some things that I know here. For example, I know that the cosine of 60 is 1/2. You also know that. Cosine of 60 is 1/2, so I'm replacing that cosine 60 with 1/2 times the cosine of theta plus, I know the sine of 60 is √3/2 times the sine of theta. Okay, now I could distribute the 20. 20 times 1/2 is 10. 10 cosine theta plus 20 times √3/2 is 10 √3 sine theta. Now this expression, this equation, y equals is in linear combination form. Well, that's it. Have fun with these things.